When we first encounter probability, we tend to treat it as a physical phenomenon, a long run of frequencies driven by chance and intuition. That intuitive framework is perfectly adequate for introductory statistics, but it collapses completely the moment we attempt to apply advanced calculus to statistical methodology. If we want to optimize estimators, take the limits of random sequences, or prove foundational theorems, we require a structure built on pure mathematical rigor. Bridging the gap between applied statistics and pure mathematics is the primary objective of André Curry's textbook, Advanced Calculus with Applications in Statistics. To truly master statistical inference, we must leave our intuition behind and reconstruct probability from the absolute bedrock of set theory. This is the cumulative distribution function, or CDF. It's a universally recognized artifact in statistics. F of x equals p of x less than or equal to x. Students learn to use this formula simply to calculate the area under a curve. But let's isolate the variable x here. In pure mathematical terms, what exactly is x? And what about this p? How is a probability mathematically bound to a variable inside an inequality? The reality is that a random variable is neither random nor is it a variable. It is a precise topological mapping. Defining the strict mathematical machinery operating beneath this equation reveals how statistical distributions are constructed. We begin the construction of a formal probability space with the universal set. This is the sample space, containing all possible outcomes of a theoretical experiment, denoted by the Greek letter omega. We populate this universe with abstract elements representing every single possible result. But a raw collection of outcomes is mathematically useless on its own. To perform calculus, this space requires a structural topology. This structuring concept is called the Borel field, or sigma field, denoted by a script b. The Borel field operates by strict rules. First, it must be closed under complements. If an event E exists in the field, its exact opposite, E complement, must also exist. Second, it must be closed under countable unions. Infinite sequences of events can be logically merged together into a mathematically valid subset. Without the topological structure of a Borel field, set operations would produce chaotic, immeasurable results, instead of valid events. Here, we see a vertical axis representing the interval of real numbers from 0 to 1. Formal probability exists as a functional mathematical measure operating on this line. The probability measure, p, is a function that maps elements from our structured Borel field directly onto this numerical interval. The first axiom of this measure dictates that the function applied to the entire universal space must always equal exactly 1. The second axiom states that for mutually exclusive disjoint events, the measure of their union equals the sum of their individual mappings. Together, this trio, the sample space, the Borel field, and the probability measure, forms a formal probability space. This functional definition of P ensures our theoretical geometry of uncertainty behaves predictably under the strict laws of advanced calculus. We now introduce the missing link between our abstract universe of outcomes and our probability measure, the random variable x. The random variable is a strictly deterministic function. X serves only one purpose: to map an abstract experimental outcome from the sample space to a specific scalar value on the real number line. Note the irony of the terminology. There is zero randomness occurring within this mapping process itself. This function translates complex real-world phenomena, whether that is a coin flip or a chemical reaction, into pure numerical syntax. The random variable function is the vital translator that converts abstract reality into a format that real analysis can manipulate. Let's return to the cumulative distribution function equation, specifically focusing on the inner condition. Capital X is less than or equal to lowercase x. We define the lowercase x geometrically as a boundary marker on our real number line. The inequality less than or equal to x describes an infinite ray spanning from negative infinity up to that boundary marker. To solve this, we rely on the mathematical concept of the inverse image, or the pullback. We trace this real number ray backwards into the sample space. This captures a subset of dots, confirming it as a valid event, safely housed within our previously defined Borel field. We then apply the final step, executing the probability measure P onto this specific subset. The pipeline is complete. The formula f of x is actually a composite function bridging three distinct topological spaces. And this composite mechanism is the only way to mathematically guarantee that probability accumulates correctly across a distribution. The exact properties of this mapping pipeline dictate the typology of the entire statistical distribution. To understand how, we look to George Cantor, the mathematician who provided the formal framework for distinguishing types of infinities and sets. Here we see Cantor's concept of countability applied. A discrete distribution occurs only when the random variable maps to an indexable set, equivalent to the positive integers. Because the mapped points are separated, the probability measure accumulates via simple mathematical summation. Conversely, a continuous distribution occurs when the mapping targets an uncountable set, a solid, unbroken interval of real numbers. Uncountability forces the mathematical framework to abandon summation in favor of Riemann-Stieltjes integration and density functions. Set countability dictates a strict topological boundary between discrete and continuous statistics. This level of set theoretical plumbing is rarely seen in daily data analysis, but it is eternally active in the background. Advanced operations, from proving the weak law of large numbers to executing maximum likelihood estimation, rely entirely on these definitions. Without the topological rigor of Borel fields and functional mapping, the entire architecture of statistical inference would collapse under mathematical scrutiny. Anchoring uncertainty in pure set theory provides the rigorous foundation necessary for statistical analysis.